In this lesson, I will explain what we're doing with radar data products to aid in understanding the mass balance. Our work constitutes the field of radar informatics. Radars are deployed on either ground or airborne platforms for data collection strategies in Greenland and Antarctica. We, however, have used autonomous platforms such as UAVs since the terrain and harsh weather provide challenges for humans operating these vehicles. This slide provides a glimpse into areas of interest for collecting data. The blue and red flight lines represent NASA and CREASA-sponsored field missions, respectively. So, you're probably wondering, how does the raw data collected correspond to a radar image? Well, I'm glad you asked. A radar trace consists of a signal representing energy due to time, and it is an entire column of pixels. The smaller figure shows a radar trace where the first largest reflection is the surface, followed by internal layers, and the deepest reflector is the bedrock. Layers in a radar imagery, which are analyzed by manual methods, are very important to domain experts since they help compute the ice thickness and accumulation rate, which are important for studying the ice sheets, their volume, and how they contribute to global climate change. We are using innovative techniques in computer vision to identifying these layers. We are interested in complete autonomy in determining layers. Since we have a large amount of data, it is not feasible for manual interpretation. There are associated challenges, however, with developing automated methods. For the bedrock surface approach, we are interested in only 2 layers, but typically these are very faint or non-existent image features. Also, false positives can hinder the correction of an accurate layer. For example, surface reflections can be repeated in an image, which may cause it to be selected instead of the correct surface layer. We have made considerable efforts to develop automated techniques for layer identification. The next few slides will highlight our work. This technique is based on a statistical framework called Markov random field models, which allow evidence from both local and global features to be combined into a single probabilistic framework for detecting layer boundaries. Another approach used in detecting bedrock and surface layers uses level sets, which is an active contours variant allowing geometric curves, in our case ellipses, to gravitate towards each boundary. The level set evolves iteratively in a normal direction to a gradient and is determined by a partial differential equation for minimizing a cost function. As the level set evolves with time, the shape of the ellipse changes to the exact bedrock and surface topography. For detecting internal layers, we used an active contours method called SNAKES in addition to a candy edge detector and a curve point classification scheme for detecting high-intensity near-surface layers while imposing constraints on smoothness and parallelism among layers.